Neutron stars are among the most extreme and fascinating objects in the universe. These celestial bodies are the remnants of massive stars that have ended their life cycles in spectacular supernova explosions. When a star with a mass between 10 and 25 times that of our Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse. The outer layers are ejected into space, creating a brilliant supernova, while the core is compressed into an incredibly dense object, a neutron star. They are stellar remnants left over after massive stars explode as supernovae. The process of their formation is both violent and awe-inspiring. The core collapse happens in a fraction of a second, and the resulting explosion can outshine entire galaxies for a brief period. The material ejected during the supernova enriches the surrounding space with heavy elements, contributing to the cosmic cycle of matter. Imagine cramming the mass of our Sun, a giant ball of burning gas, into a sphere with a diameter of just a few miles. This is the reality of a neutron star. Despite their small size, neutron stars pack a punch with their immense density. A neutron star's mass is typically about 1.4 times that of the Sun, but all this mass is squeezed into a sphere with a radius of only about 10 kilometers. This is the reality of a neutron star. Their immense density creates incredibly strong gravity. The gravitational pull at the surface of a neutron star is about 2 billion times stronger than that on Earth. This intense gravity can bend light, a phenomenon known as gravitational lensing, making neutron stars appear distorted when observed from a distance. Neutron stars are so dense that a teaspoonful of their material would weigh billions of tons on Earth. To put this into perspective, imagine compressing the entire human population into a sugar cube. This extreme density is due to the fact that neutron stars are composed almost entirely of neutrons, subatomic particles that are packed together in a way that defies our everyday experience of matter. This extreme environment makes them natural laboratories for studying the fundamental laws of physics. Scientists use neutron stars to test theories of gravity, nuclear physics, and quantum mechanics. The conditions inside a neutron star are so extreme that they cannot be replicated on Earth, making these celestial objects invaluable for scientific research. Neutron stars emit beams of radiation from their magnetic poles. These beams are incredibly powerful and can be detected across vast distances in space. The magnetic field of a neutron star is trillions of times stronger than Earth's, and it channels particles along the magnetic poles, creating intense radiation beams. As they rotate, these beams sweep across space like a lighthouse beacon. If the beam points toward Earth, we detect it as a pulse of radiation. This is why neutron stars are often referred to as pulsars. The rotation period of a neutron star can range from milliseconds to several seconds, and the regularity of these pulses makes them excellent cosmic clocks. We detect these pulses of radiation as rapidly flashing signals, hence their name, pulsars. Pulsars have been used to test the theory of general relativity, search for gravitational waves, and even navigate spacecraft. The precision of their pulses allows scientists to measure time with incredible accuracy. The study of neutron stars continues to unlock secrets about the universe. Each discovery adds a piece to the puzzle of how the cosmos works. From understanding the life cycles of stars to probing the nature of matter under extreme conditions, neutron stars are at the forefront of astronomical research. They provide insights into the life cycle of stars, the nature of gravity, and the origins of heavy elements. By studying neutron stars, we learn not only about these fascinating objects themselves, but also about the broader workings of the universe. Their extreme conditions offer a unique window into the fundamental forces that shape our cosmos. Stars are engaged in a constant battle between gravity and outward pressure. Gravity tries to collapse the star, while nuclear fusion in the core generates energy that pushes outward. For most of a star's life, these forces are in equilibrium. However, when a massive star, much larger than our Sun, exhausts its nuclear fuel, this balance is disrupted. The core collapses under its own gravity. This collapse triggers a catastrophic explosion known as a supernova. During the supernova, the outer layers of the star are blasted into space. Meanwhile, the core continues to collapse. The protons and electrons in the core are forced together under immense pressure. They combine to form neutrons, creating an object composed almost entirely of these neutral particles, a neutron star. Neutron stars are incredibly dense. They pack a mass greater than the Sun into a sphere with a radius of only about 6 miles. To put this into perspective, imagine squeezing all the people on Earth into a single sugar cube. This extreme density results in some bizarre properties. The gravitational pull on a neutron star's surface is about 100 billion times stronger than Earth's gravity. Time itself is affected by this intense gravity, slowing down near a neutron star compared to time on Earth. The internal structure of a neutron star is still not fully understood. Scientists believe it consists of a superfluid core of neutrons. This core is surrounded by a crust of heavy nuclei and a thin atmosphere of charged particles. Section 4, a pulsar surprise, Jocelyn Bell Burnell and the discovery of rotating neutron stars. In 1967, Jocelyn Bell Burnell, a graduate student at the University of Cambridge, made a remarkable discovery. At the time, she was working under the supervision of Anthony Hewish, a renowned radio astronomer. The project involved using a large radio telescope to map quasars, which are extremely bright and distant objects powered by black holes. Little did they know their research would lead to one of the most groundbreaking discoveries in astrophysics. While meticulously analyzing the radio telescope data, Bell Burnell noticed something unusual. Amidst the noise and signals from various cosmic sources, she detected a series of regular pulses, like a cosmic heartbeat. These pulses were incredibly precise, repeating every 1.337 seconds. This regularity was unlike anything seen before and immediately caught her attention. These pulses were coming from a single point in the sky and repeated with remarkable precision. The regularity and consistency of the pulses suggested that they were not random, but rather originated from a specific astronomical source. This was a significant clue that pointed towards a new and unknown phenomenon in the universe. Initially, the signals were jokingly dubbed LGM-1 for little green men, hinting at a possible extraterrestrial origin. The idea of intelligent alien life sending signals to Earth was both exciting and humorous to the scientific community. However, the team knew they needed to investigate further to understand the true nature of these mysterious pulses. Bell Burnell and her supervisor Anthony Hewish meticulously analyzed the data and conducted additional observations. They soon realized that the signals were not from extraterrestrial beings, but from a new type of celestial object. This discovery was groundbreaking and led to the identification of pulsars, a term coined to describe these rapidly rotating neutron stars. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. These beams are incredibly powerful and can be detected across vast distances in space. As the neutron star spins, these beams sweep across our line of sight, creating the observed pulses. This phenomenon is similar to a lighthouse, where the rotating light beam is seen as periodic flashes from a distance. The discovery of pulsars was a monumental achievement in astrophysics. It provided the first observational evidence for the existence of neutron stars, which were previously only theoretical. Neutron stars are incredibly dense remnants of supernova explosions with masses greater than the Sun but compressed into a sphere only about 20 kilometers in diameter. The study of pulsars has since opened up new avenues of research in understanding the extreme conditions and physics of these fascinating objects. The discovery of pulsars not only advanced our knowledge of the universe, but also highlighted the importance of meticulous observation and analysis in scientific research. Jocelyn Bell Burnell's keen eye and dedication to her work played a crucial role in this groundbreaking discovery. Her contribution to astrophysics has inspired generations of scientists and continues to be celebrated as a milestone in the field. Section 5. Listening to the cosmos. Studying neutron stars with radio and gravitational waves. Scientists use a variety of methods to study neutron stars. These incredibly dense remnants of supernova explosions are some of the most fascinating objects in the universe. By employing different techniques, researchers can uncover the mysteries of these stellar remnants and gain insights into the fundamental laws of physics. Radio telescopes are crucial for detecting the pulses from pulsars. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation out of their magnetic poles. As these beams sweep across the Earth, they can be detected as regular pulses of radio waves, which provide a wealth of information about the pulsar's properties. By analyzing the timing of these pulses, astronomers can learn about the rotation rate, magnetic field, and even the mass of neutron stars. The precision of these measurements allows scientists to test theories of matter under extreme conditions, offering a unique laboratory for studying the fundamental forces of nature. In recent years, gravitational wave astronomy has opened a new window into the universe. This groundbreaking field allows scientists to observe cosmic events that were previously undetectable, providing a new way to study the most violent and energetic processes in the cosmos. Gravitational waves are ripples in space-time caused by the acceleration of massive objects. These waves travel at the speed of light and can pass through matter without being significantly altered, making them perfect messengers from the distant reaches of the universe. When two neutron stars collide, they generate powerful gravitational waves that can be detected on Earth. These collisions are among the most energetic events in the universe, releasing vast amounts of energy in the form of gravitational waves and electromagnetic radiation. The first detection of gravitational waves from a neutron star merger in 2017 was a landmark event. This discovery not only confirmed the existence of gravitational waves, but also provided a new way to study the universe, combining observations of both gravitational waves and electromagnetic signals. It provided a wealth of information about these extreme objects and confirmed several key predictions of Einstein's theory of general relativity. This event marked the beginning of a new era in astrophysics, where multi-messenger astronomy allows scientists to gain a more comprehensive understanding of the universe.